Welcome, Kashufi, Petro.
Dr. Nyosi,
Yes.
uh, yesterday you said you're going to post something about the second homework that you're doing, but you did not post it.
Oh, yes, you are right. But I enroll all of you. I hope you receive a message of enrollment for the platform. I mean the e-learning.
Nope.
Okay, but you can now have access to the e-learning platform because I enrolled
The
everybody.
Oh, okay.
I think
Who
some
did
of
you
you
give?
told me that you were facing problems, access problems to the e-learning platform.
Oh no, the
Am I
last
right?
time I logged into the e-learning, I only saw the one for last year.
Also, you
That
succeeded in
wasn't
logging.
that wasn't updated.
Ah, okay.
So is it the same one? Or
Yes,
you
yes, 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 yes. It's the
okay.
same. It's the same. I still need to
I
update
know if
that.
it's the same, then I have access to it.
All right.
Yeah.
Because you will see, no, it's semester two. No, 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 no. It is written semester two, 2021.
Oh, 2021.
Yeah. But the all contained is still there. It's still available.
Oh, so I can even check now to confirm.
Okay, check and let me know.
Mm-hmm.
Once again, good afternoon to all of you, and welcome to this other edition of our numerical method class. I think today is the 13th edition. So yesterday I introduced the concept of the Fourier series, but before that we defined what is a periodic function. We saw that the function is periodic if it takes the same value after a certain period of time or space, right? Like here, a function of real variable x is periodic and of period p if each time you add p to x, you still get the same value as f of x, right? Okay, and a simple case of a trigonometric function which is periodic is a cosine function. Uh, if you use the formula for cosine and you compute cosine of x plus 2 pi, you still get cosine of x. It will give you exactly the same results. And how do you see it? You can simply draw the trigonometric circle, fix a certain point, rotate by 360 degree, which is 2 pi in radian. It will give you the same value. So it shows that the cosine function and the sine function are both periodic. Okay, from that we define what is the Fourier series of a function that is periodic and of a period 2 pi. And that function has to be piecewise continuous over a certain interval or an interval of length p, which is a period. But since we fixed the period to be 2 pi, if you look at this interval negative pi pi, you can see that the length of this interval is 2 pi, which corresponds to the period of the function. So the Fourier series of this function f is defined by s sub f of x equal to 0 and a0 by 2 plus this summation k running from 1 to infinity ak cosine kx plus b sub k sine kx, where the coefficient ak and bk's are given by what we call Euler's formula, and they are given by this expression. As you can see, the range of k runs from 0, 1, 2, 3 up to infinity, but for bk, k runs from 1, 2 up to infinity because b0 is not defined. Okay, So in this definition of the Fourier series, there's no mention of the convergence of the series. So for some x, you can even get infinity. Now, this is just a definition. Now, when it comes to convergence theorem, there's a statement, there's a theorem. Fourier expansion theorem, which gives us a condition for the Fourier series of x to converge towards f of x for a certain point x. So for that, you need the derivative to satisfy extra condition, right? Beside the fact that the function f, which is 2p periodic, has to be continuous, piecewise continuous on the interval negative by pi. You also have a condition of the first derivative. First derivative has to be also piecewise continuous as f, or like f. And beside that, you need the left and the right derivative of the function at each point. I mean, f prime, which is the derivative, right? It has to admit the left hand and the right hand derivative at each point of the interval negative pi pi. Meaning that if I take a point in the interval negative pi pi, any point in that interval, the derivative I will write it somewhere here. What that means. Okay, so if you say left and right derivative, right, have to exist. Now, if I take this limit, I take a point, let's say x0, I take an arbitrary point on this interval, then f prime x0 minus has to exist, and f prime x0 plus, these 2 points have to exist. That is what means the left and right derivative. And this one, the left or right derivative, we define something similar with f. So this means that the limit of f prime x, when x tends to x0, from the left, like this. So you take x from the left of x0, and then you let n tends to x0. That will give you the left limit. And similarly for the right limit, you start from the right of x0, and then you push x towards x0. So you look at the result of that limit. If they exist, then these two conditions are satisfied. They don't need to be necessarily the same, right? They might coincide, they might not. But the most important thing is that those two limits have to exist, the left and the right. Okay, so if this condition is further satisfied, then the series that we define here, this is a series that depends on x, it will converge. Converging means that that series will converge to a fixed real number, which is not infinity. Okay, you know what it means to converge. So it converges as a sequence. Okay. Now, we know what the points of discontinuity of x are. If you look at this example, you can see that all these points, negative 5 pi, negative 3 pi, negative pi, 3 pi, and all those points are points of discontinuity, because you can see that here at negative pi, sorry, at pi, there are two values that the function can take. You have this one and you have that value on top there. So there's a jump at this position. So the function is not continuous here at pi, at all these points. So these are points of discontinuity. But if I'm here in between these 2 points, that's from pi to 3 pi, you can see that the function is continuous. You see. So that's where the first condition has to be satisfied here. Negative pi pi. And of course, by extension of the periodicity, it will also be true in the other interval when you extend. But remember that we fixed our interval negative pi pi, we work on that. But by periodicity will be true because we'll be extending by translation. Okay, now at the points of non-discontinuity, I mean, the point of discontinuity or the point of non-continuity. So at this point, the sequence or the series will not convert to f of a, but it will converge instead, because if the point is discontinuous, it means that the left and the right limits exist and they are not the same. That's why they are discontinuous. If they are continuous, these two will coincide, they will be the same. So if f of a minus is the same as f of a plus, that's exactly what we call f of a, because they will add up to be 2 f of a, and 2 in the numerator and 2 in the denominator will cancel out. Then it will give you f of a. But it doesn't convert to f of a because f of a does not exist. At a, there are two values, the left value and the right value. That's the point of discontinuity. So at the point of discontinuity, the sequence will convert towards the average of the left and right limit. This is the average of the left and right hand limit. But if f is continuous at that point, it will be f of that point. Okay, so this being said, I ask you to go through this example. So I ask you to read and prepare for what we are going to do today. So having set the stage, you can now dive into the problem. Now, if you look at that function, the way the function is defined, in itself, the function is not periodic, but we extend it periodically to make it periodic, right? Because we are dealing with periodic function. So we are given a portion of the function in the interval negative pi pi. It can be anything. Now, because the function we are dealing with are periodic function, we extend that definition, that is x by 2, which is defined over the interval negative pi pi. So we extend that all over the real line by translating to the right and to the left to obtain a periodic function, because our function f has to be periodic. So that's what is happening here. So what are we going to do? We use the formula, which is this one. We can also compute the derivative on this interval. negative pi pi. So this is our function. If we compute the derivative of this, it gives us a constant function 1 by 2, which is a constant function on that interval. So you see that the left and right hand side limit, derivative will exist. Because it's constant. The derivative is 1/2. So at any point to the left and to the right, the derivative will be exactly the same. So after the previous theorem, the theorem that Fourier expansion, there will be convergence of our series. At any point in that interval negative pi pi, there will be convergence. And the difference will be where? At the point of discontinuity. And at the point of discontinuity, the sequence, this one will converge towards the average. Okay, now we can write, we can therefore use this one when x is in the interval negative pi pi. And then we use our formula. So we have this formula, which we can write down. And then the next thing is just to compute our AKs and our BKs. Obviously, I know already that AKs will be 0. Obviously, I will not tell you for now why, right? But we'll see that later on. But we can still compute for you to see that the AKs will be 0. Only the BKs will be non-zero. Okay. So for the AKs, let me do the computation. Right. Anyway, this is just integration by part. There's no mystery here. There's no witchcraft. So anybody can see. Anyway, you did calculus 2, so you should be able to compute this integral. So if you compute the integral, that's exactly what you get. Now, if you substitute, maybe that's what I will do now, the substitution. For each one of you to see that it gives 0. Some of you might not see, because you don't have that kind of eyes to see. Right. So that's what I'm going to do now. So that some of you will not go back home and cry. You start crying. Or your neighbor will see you. Why are you so sad? And you start telling stories. Oh, our lecturer is not serious. He came with something that we have never done. He said that we should do it. I've been trying, I've been thinking, but I cannot understand. I'm lost. Huh? You are lost? You will be found. Okay. So I'm going to open a new window, I'm going to share. The secret of Fourier series is integration. Huh? So if you have problems with integration, you have to go back and read your note on integration, because you cannot escape integration. You see that your AKs and BKs, each time you need to integrate. And if you can't integrate, start crying. Lament on your fate. But it's not late, eh? Just go and revise. If you are here, it's because you passed calculus 2. So you just need to revise. Okay, so we have Fourier series. So we know that our function f of x is given by what? X by 2 for x in the interval negative pi pi. Right? And we assume that f is 2p periodic to 2 pi. Two pi periodic, meaning that the period is 2 pi. 2 pi periodic. Periodic of a period 2 pi. Obviously, you can see the function is continuous. It's piecewise continuous because it's continuous on this piece, negative pi pi, and then by translation, you see that if the function is increasing like this, regardless of the shape, if you translate it, you see that there's already a discontinuity. So it will be piecewise continuous, continuous only in a sub-interval, not throughout. And there will be point of discontinuity. So it's piecewise continuous. All right. So this is our function. Now the AKs, we know already that. Okay, let me write. SFX. That is our Fourier series by definition. Even though we know that this will converge to f, right? But the definition itself, it is A0 by 2 plus, now we have a summation, where k will start from 1 to infinity. Now, here we have a combination of AK cosine kx. You see that the k that varies is here. And because it's a function of x, you need also x there. So it's a function of k and x plus, now we also have the bk. Now this time it will be sine k and x. So if you forget k, it's wrong. If you forget x, it's wrong. You have both k because you have a summation over k here, and you also have the variable x here. So you have both x and the variable k. So you have k and x, k and x, and then you also have your bk, ak. Good. Now, what is your ak? Because for ak, you see that k can take the value 0 because a0 is defined, right? So it is 1 by pi, then the integral from negative pi to pi here, fx. Now, because ak is a factor of cosine here, you also have cosine here. Kx dx. Now k will take the value 0, 1 up to infinity. Now for bk, it is similar, you just change cosine into sine. So just copy from negative pi to pi, f of x sine kx dx. Now k starts from 1 because b0 does not exist. Good. Now we know already that from negative pi to pi, I know the expression of my function. And since in the definition of my A case and B case, the interval is from negative pi to pi, I just substitute. If the function was defined differently, for instance, if I had the expression of the function from negative pi to 0, and then from 0 to pi, this will mean that I will have to split this interval from negative pi to pi accordingly and substitute the various or the corresponding value of f for each subinterval. So this does not mean that if I have my function defined on various intervals, I will still plug that same function here. No, you have to split this interval accordingly. I want that to be clear, because in some tests, I realized that when you give a piecewise function defined with different values, people don't even know how to split this interval to substitute the corresponding expression of f. This just indicates that the person does not understand integral at all. I can substitute this directly because my interval here is from negative pi to pi, and the expression of my f is exactly on that same interval. You see that these two intervals, negative pi to pi, and this will coincide. You see that they are coinciding. So I can substitute this value directly. But if I have two different or three different or four different expressions of my f, I will come and split this interval accordingly, and for each subinterval, I substitute the corresponding expression of f. Because I know that from the expression of the integral, I know that if I have an integral from a to b of, say, the function f of x, let's say that on the interval, let's say, for instance, this is how my function f is defined. From, let's say f is 1, from a1 to a2, then the function is negative 5 x, for instance, from a3 to a, let's say, 4, and then 0 otherwise. Obviously here my a0 is greater than or equal, let's say greater than, a is less than or equal to a1, a is less than or equal to a1, and then this one, a4, is less than b. Anyway, you will know from the actual value, I'm just taking generic values. Now, if I want to evaluate this integral I using this expression, it is obvious that I have to split this interval, because I know Chasles rule. Chasles rule tells me that I can break this as many subintervals as I want, provided they add up to whatever is there. So I can write this as, because I have this, I can write that this is the same as if I start from A and then I reach A1. You see? Plus, now I can integrate from A1 to A2, plus A2 to A3, plus So now from A3 to A4, right? And finally from A4 to B. To B. So this is choiceless relation. That this is from the integral. I can do this for a finite number of endpoint because I know that if there's C in between, the integral from A to B, I can split as integral from A to C plus integral from C to B. If I can do that for a single, I can do for a finite number. So that's basically what I did here. Now, if I substitute, I only have these two values, the rest is 0. So it's 1 from negative, from A1 to A2. So from A1 to A2 here, F here is equal to 1. Now from A3 to A4, A3 to A4, F here is equal to negative 5x and 0 elsewhere, meaning that this will be 0, this will be 0, and this will be 0. So I keep whatever I just look at the expression and the interval that are given here. I split whatever interval I have here accordingly, and I substitute. So this integral will end up being the integral from A1 to A2, and then you have the 1 here. So dx plus or minus, because this is negative, okay? Or I can say plus. Now the integral from A3 to A4, negative 5x dx. So I'm explaining it like this so that you never write something that doesn't make sense in Fourier series, because you need to know integration. Please go and read. I will not tell you everything because these are supposed to be known by you. But I'm stressing on this because students have been making that mistake. They don't know when you give them a piecewise function like that, they don't know how to substitute in the integral, which is really unfortunate. All right. So that is it for this part. So now let me, because this is what we want to do, we want to compute our AKs and BKs. In this case, there's no problem because the function is already is only one piece on the integral on the interval negative pi. So you will not have this issue. But if the function, as you even see in the tutorial sheet, you will see that for some function, you have two sub-intervals. It can even be 5, even 10. It depends on the problem. But you should be able to substitute. Okay, in this current problem, in this current case, there's no problem because the interval, negative pi, only has one expression of the function. So you just substitute it blindly. Okay, so this one is just this is a particular case. Huh? This was just for explanation purposes. Okay, so now let's go back to this one. So let me, okay. Anyway, anyway, for this one, for the AK, I don't need to redraw that because we know already. Sorry, we know already the expression. So. So I can already substitute this. So this is just so what is the value of f of x over the interval negative pi is x by 2. So I can substitute x by 2 like this, and then cosine kx dx. All right. Okay, but now integration by part. So what I would do, since this is x, I will lower the power by differentiating, and I will integrate this one. And then I will have a simple expression. So this is my u, and this is my vd dv. You can see that, of course, this is a constant, 1 by pi. I can take it inside, I can keep it outside. So integration by part, I keep this factor 1 by pi outside. Now I perform integration by part to this integral. So this is integral u v dv. No, sorry. The v is not there, it's just u dv. So I need, of course, you know that here, if this is v, okay, let me write it. So what I mean is that I keep the 1 by pi, and then what is inside here is my integral u dv from negative pi to pi. So this is what I'm integrating, where u is this 1 by x. Okay, now we know that this integral, the inner integral, will become uv from negative pi to pi minus the integral. Now it will be v du. So that's integration by part. Integration by part. Okay. Now, so this will be equal to 1 by pi. Now uv. This is u is x by 2. And now what is v? V is just sine kx by k. You see, now for me to divide by k, I have to make sure that k is not 0. So what I'm writing here is for k non-zero. Otherwise, if k is 0, you see that cosine will be 0, and I will just integrate this one directly. So if I write this, it's for k non-zero. Otherwise, I cannot divide by 0. So here I will say this is true when k is non-zero. That's when I can write this. Okay, so this factor of this, I will evaluate it from negative pi to pi. Now I have minus. Okay, so I already have my v. This is v. It's already there, so I can substitute it directly here. Now I will differentiate this one, du. So if u is this, if du will be 1 by 2. So this would be 1 by 2. I can take it out if I want. 1 by 2 for this, and then dx. So inside the integral, I have v, which is this one, sine kx by k into dv. Okay, for dv, du is dx by 2. So I already took these two out. Then I have dx. So this is what we have here. Okay, since this is a single function, I can find its antiderivative directly. So this is equal to, let me continue here. So that is equal to what? 1 by pi. Now, if I substitute this inside this one, I have x equal to pi, and the next will be negative pi. Okay, now, because the sine function is an odd function, this negative will go out. With a negative, it will become plus, so it will be let me put it properly. So the first time when it's pi, I have pi here and I have pi inside, right? And then minus in front. Now this pi will make it plus, and the negative pi, so it will come outside, so they will cancel out directly. It will cancel out directly, so this will be 0. It will cancel out directly because of that. Okay, let me write everything. So this is 0. So to see that, let me write everything here. So the first one takes the value pi, I have pi by 2. Pi by 2 sine k pi by k. Okay, now then there will be minus the same function at negative pi. Now, when x will be negative pi with this, okay, let me put negative pi here by 2, and then sine of negative k pi by k. Now, this because sine is an odd function, this negative and this negative will cancel out, then become positive like this. Now you can see that this expression is the same as that one, to cancel out for this one. Okay, now minus, so that's why I say they cancel out. So this will cancel out with that. Okay, minus for this 1 by, okay, I can take even this k out, so that will be negative 1 by 2k. So I'm taking this k out. Okay, now what is the antiderivative of this? The antiderivative of this will be negative cosine k x by k. So that's the antiderivative of this one, of the sine k pi, sine kx. So the antiderivative of sine kx is this one. And that is evaluated from negative pi to pi. And then I can close the curly bracket. Now we are going to evaluate this. Okay, you can see that this negative with this negative also. This is a multiplication. You see. All right. So now I will only evaluate this because these two cancel out. So this will be equal to 1 by pi this factor. Okay, now inside the curly bracket, I will evaluate this. Okay, so I can also take this k out, right? So the factor, the common factor here will be 1 by 2k squared. 1 by 2k squared into. Now, I will evaluate this at this point minus at that point. Is that clear? Good. So if I evaluate, of course, we also take into account the fact that the cosine function is an even function, right? So let me substitute. So at cosine, here I have cosine k pi for this one, and then minus cosine negative k pi. You can see that this also will cancel out because this will be absorbed because cosine is an even function, it will be absorbed. You can see that this minus itself gives 0. So this also is 0. So this cancel out with this one, and it is identically 0. So in fact, it gives 0. And that is true for what? For k non-zero, meaning that k 1, 2, up to infinity. Now we need to compute explicitly the case k equal to 0 because we divided by k, so k cannot be 0. Now, if k is 0, a0 will be what? F of x, right? To be the integral f of x dx, because the factor here with cosine is 1. Cosine of 0 is 1. So this is what you have, which is 1 by pi, integral from negative pi to pi, and we know that this is x by 2 dx. And what is this? I can take these 2 out, right? If I take the 2 out, the integral of that will be x squared by 2. X squared by 2. So this will be 1 by 4x, sorry, 4 pi x squared here. You see? From negative pi to pi. But this is an even function, so x squared for x equal to pi, it will be pi squared minus negative pi squared, 0 again. Right. So ak is completely 0 for any k. Identically for any k, including 0. Okay, so that is it for this one. So ak is always 0. But I will explain to you that there was no need for us to do all this computation, right? We could have just computed directly our bk. But it's fine, we can leave it that way. If you don't know, you just compute. But we could have seen directly that the function, this function, is an odd function here. It's an odd function here. So even when we extend it periodically, it will remain odd. An odd function can only be expanded in terms of odd function. So between cosine and sine, the odd function is sine, meaning that the term in cosine will not be present. So only the terms in bk will be present. So all the ak's not automatically will be 0. Okay, that's another way to see it without even computing. Okay, now let us do the computation for bk. We know the formula for bk. This is the formula with the sign, this one. And k starts from 1. Right. So we will do something similar to this integration by part here. we will do something similar. So let me copy this. We'll just modify it a bit. Okay, so I can just change here, change this one, change this. So this is BK, this is sine. So we have that. So now when we come here, so U is still the same. But this V that would change. Okay, so equal to 1 by pi here, the factor, and then inside. So U is still the same, x by 2. Now, what is our V? Our V will be negative cosine kx by k. And it's good because k cannot take the value 0. K starts from 1, right? So there's no problem here. So I can write it directly. So this is my U, this is my V. And you can always check. If I differentiate this, I should get dV. Now, if I differentiate cosine, it will become negative. With this negative is positive, and then sine. The k will multiply, and that k will cancel out with the k in the denominator. So I will get this. So it's correct. I don't need to stress. Now we have from negative pi to pi here, and then minus this one. Now we integrate v du. Okay, du as usual will be dx by 2. So I can take that 2 here. We are left with dx here. And now what is our v? This is v. V is already present here. Just copy. This negative with this negative become positive. Plus there, I can change it. And then I substitute that inside. Cosine kx by k. And I can quickly rearrange and take that out. So I can take this k out. So that's 1 by pi. Right. Okay. Even this negative, I can take this negative out. Right? I can take that out. Now, this will still be 0 because if you recall, if I take this negative out here, oh wait, it might not be 0 because of this, right? Yeah, because the sign will change here. It will change here with the sign. I cannot just, okay, let me put the negative out here and then this positive. Okay, now let me substitute directly. So for pi, this will be, okay, I will take this 2 and this 2 out. So I have 2 pi out here. Okay, so I say that this is plus and this is negative. Okay, now if I take pi, it will be negative pi here, and so negative pi and cosine k pi. Now, minus, with this one, it will be positive, but with this minus, it becomes minus again here. Pi cosine k pi. Now, same thing, so it becomes negative 2 times this one. Right, okay, so that is it for this. Now, for this one, I took the 2 already, a factor here. Now, what is the antiderivative of this? Okay, I can take this outside, plus 1 by k. Now, if I take the antiderivative of cosine kx, it will be sine kx by k. So that will be square here. And that will be from negative pi to pi. Okay, good. But what is this? This is an odd function. Center at 0, so this will be 0. So this will cancel out completely. So all this is 0. You all agree with me, huh? Because no, what did I say? Yes, I'm right. Oh, no, sorry. This is not an integral, it's already just a substitution. So it will be this at that point, minus, it becomes 2 times this. Okay, so it's not 0, sorry for that. I dealt with as if it was an integral. It was not an integral. So this is equal to, so I can write directly. So this is 1 by 2 pi. Okay, so all this is negative 2 times cosine k pi for this one. Okay, now for this, I have as a factor 1 by k squared, right, this one. And then inside I have sine, that would be 2 sine, 2 sine k pi, right? Because there will be a minus here, with that minus it becomes plus, and then there will be a 2 here in front. Good. Now, sine k pi, so this is my trigonometric circle. So I can already tell you that this will always be 0, this one. Because if k is equal to 1, sine of pi is 0. If k is equal to 2, sine of 2 pi is 0. Sine of 3 pi, 4 pi, so it will oscillate between these two positions. That is, this is my trigonometric circle. It would be here or there. And this is the axis of the sine. It will always be 0. So this is always 0. So I will be left with this one. And I express that simply. So this is reduced to, okay, so this 2 pi, we cancel out with this one. So it will be negative. So this is negative cosine k pi. And cosine k pi is what? Cosine k pi, so you have negative here, it is negative 1 to the k. So this is negative 1 to the 1, I will add with this one, so it's negative 1 to the k plus 1. So that is the value of what? Of my bk, eh? Okay. So this is the value of my bk, negative 1. Okay, why is it that so? Cosine k, if k is equal to 1, cosine of pi is negative 1. So that's why you have that negative. Now, if k is 2, cosine of 2 pi is 1. So it will oscillate between negative 1 and 1, depending on the value of k. So if k is odd, it's negative. If it's even, it's positive. So that's why you have that. With this negative, you will add the power. So that's what you have. So that is the final result for the decay. I hope I did not fall. I did not forget anything in that. What is the oh, so sorry. There is this K that I did not take this K into account. This one. Do you see this K? So this K is factor here, 1 by K. So it's divided by this K. So by K by K. So now we just substitute, therefore, so that is our decay. So therefore, we can just conclude that our f of x is equal to this summation from 1 to infinity. So the bk and sine. So I take this negative 1k plus 1 by k sine kx, and that is it. That's the final result. Okay, so we'll stop here for today. If there's no question, I think we will stop here. Is there any concern, any question? So far, so good. Is there any question? Okay, so if there's no question, we'll stop here for today. Thank you so much for your kind attention. God bless you and see you tomorrow. Yeah, tomorrow. Is it tomorrow? Yeah, you have a class tomorrow. Bye.